Welcome to the Deep Dive, where we transform complex topics into digestible insights. Today, we're taking a deep dive into the enduring legacy of Euclid, a name, well, pretty much synonymous with geometry.
Absolutely. Cornerstone stuff.
Exactly. But what if we told you there's a version of Euclid's Elements that isn't just about ancient proofs, a version that actually acts as a bridge to modern mathematics, and it's packed with some really surprising insights and even practical applications.
Intriguing. Which version are we talking about?
We're focusing on John Casey's first 6 books of the Elements of Euclid, specifically the third edition, revised and enlarged, published back in Dublin, 1885. So what exactly was Casey trying to do with this edition? What made it so, pivotal for students back then?
Well, Casey's vision was really quite ambitious. He wanted to present Euclid's original work, the unrivaled original in all its integrity, as he put it.
Okay, preserve the classic.
Right. But, and this is the key part, he wanted to combine it with modern conceptions and developments. His goal was essentially to make this foundational text relevant, accessible for a new generation. He brought in insights that were pretty cutting edge for the time.
So it wasn't just a reprint.
Oh, definitely not. It was seen as a necessity for the student, really, because it offered this unique blend of historical rigor and, well, forward-thinking mathematics.
That sounds like a powerful mission for what's essentially a textbook. So our deep dive today is all about pulling out those key nuggets of knowledge, those insights from Casey's work. We want to help you understand why this particular edition of Euclid is, frankly, still fascinating today.
Sounds good. Where should we start?
Let's go right to the beginning. Euclid's foundations. How does he even define something as basic, as fundamental as a straight or right line?
Okay, yeah. Well, Euclid starts with pure abstraction. And Casey actually highlights this great illustration from a Professor Henrici.
Oh, yeah. What was it?
Henrici described a straight line as being like a stretched string. But then, and this is the crucial mental step, you have to abstract all thickness from that string. We're left with this ideal, perfect geometric line. It's completely detached from any physical sort of imperfection.
That's a really helpful way to visualize it. Taking away the physical, does this same idea, this abstraction, apply to something like an angle? That seems so fundamental, too.
It does, yeah. Euclid usually focuses on the smaller angle, the one less than 180 degrees formed by two lines.
Right.
But what's interesting, and Casey points this out, is that Euclid kind of subtly acknowledges the reentrant angle, the bigger one on the outside. He mentions it seldom occurs in the elements, which sort of hints that he was aware of this broader concept of angles, something that became much more important later on in math.
Huh. So it's not just what he includes, but what he sort of nods towards. That leads perfectly into Euclid's postulates and axioms, those basic assumptions geometry is built on. Why did Euclid feel the need to say, let it be granted, that a line can be drawn or extended or a circle described? It feels almost obvious now.
Yeah, it does seem obvious, doesn't it? But this is where Casey provides a really insightful note. He explains that if you physically drew a line, say with a ruler and pen, it would inevitably have irregularities, breadth, thickness, little imperfections.
Sure, of course.
Those are not truly geometrical lines. Euclid's postulates show this deep understanding of geometric precision. He's dealing with ideal abstract concepts, not flawed physical things. If you could actually draw a perfect line physically, you wouldn't need to ask us to grant it. It's about conceiving of perfection.
I see. Wow, that's a really deep point about the pure nature of Euclidean geometry. And what about the axioms, those self-evident truths? Axiom in eighth stands out. Magnitudes that can be made to coincide or equal. What's the core idea there?
So this is the concept of superposition. But Casey is careful to clarify this isn't a physical act. It's only mental.
Okay.
You imagine placing one shape perfectly on top of another. If you can mentally reason that they coincide exactly, then you deduce they must be equal. This axiom kind of implicitly contains the idea that you can move a figure around, transfer it from one position to another without change of form or size, which is absolutely fundamental for proving congruence without needing, actual cutouts.
Right, purely a thought experiment. Okay, so we've laid the groundwork, these fundamental building blocks. Let's move into exploring figures in 2D. Book Wime, for instance, deals with triangles. Most people probably remember the classic proof about isosceles triangles, the base angles being equal.
Oh, absolutely. Proposition V. It's a classic.
ahead.
And Casey doesn't just, repeat Euclid verbatim. He uses this context to introduce a more modern idea, the axis of symmetry.
Ah, symmetry.
Yeah, a line you can fold a figure across so it perfectly matches up with itself. You can easily see this with an isosceles triangle. or maybe a lozenge, that's a rhombus, a shape with 4 equal sides.
Okay.
And he also defines the median of a triangle. That's the line from a vertex to the middle of the opposite side. And here's a neat little insight from Casey's exercises. He points out that the sum of the 3 medians of any triangle is always less than its perimeter.
Really? Less than the perimeter? That's not immediately obvious.
No, it isn't. It's one of those subtle geometric inequalities that takes you a bit beyond just the basic properties. It shows how Casey was adding value.
I like how he bridges the classic proofs with these more modern, intuitive ideas like symmetry and these cool inequalities. Let's jump to book 2. This one often gets into geometric versions of algebraic identities, right? Like proposition IV showing a plus b or a plus b plus 2ab geometrically.
Exactly. The square on the whole line is equal to the sum of the squares on the parts, together with twice their rectangle. Classic geometric algebra. And Casey notes there's a general corollary for dividing a line into any number of parts. But maybe the most fascinating part of Book 2, connecting to the bigger picture, is proposition X. It's framed as a problem.
A problem, not a theorem.
Right. It asks you to construct something, to divide a given finite line, so that the rectangle contained by the whole line in one segment may be equal to the square on the other segment.
Okay. What does that actually mean?
That describes division in extreme and mean ratio. We know it today as the golden ratio.
Ah, the golden ratio. So Euclid shows how to construct it.
Precisely. It's presented as a practical construction problem, not just an abstract number. It's quite amazing it pops up so early.
That is cool. And Casey also points out something about Euclid's structure, doesn't he? About pairs of propositions.
Yeah, he observes that some pairs, like propositions 4 and 7 or 12 and 13 in Book 2, are virtually identical when viewed through the lens of modern geometry. It really shows Casey trying to synthesize things, make connections clearer for students of his time.
Makes sense. Okay, moving into Book 3, we're entering the world of circles now. How does Euclid define a tangent differently from how we might think of it today?
Well, Euclid's definition is quite strict, quite static. A tangent is a line that meets the circle but does not cut it, just touches at one point.
Right.
Modern geometry, influenced by calculus, has a more dynamic view. It sees a tangent as a second, a line cutting through 2 points, where those 2 points have become consecutive, meaning they're infinitesimally close together.
Consecutive points. That sounds very abstract. Can you, give an analogy?
Sure. Imagine a line slicing through a circle at 2 distinct points. Now, picture those 2 points sliding along the circle towards each other, closer and closer, until they basically merge into a single point. The line passing through that merged point is the tangent.
Ah, okay.
Like the limit of a second line.
Exactly. It's a conceptual leap, born from calculus, that goes beyond Euclid's more static picture.
Got it. And even with these ancient theorems, there are some neat practical uses. You mentioned proposition XXXI. Something about finding the center of a circle with a Carpenter square. How does that work?
Oh, it's brilliantly simple. You take a standard Carpenter square, with the 90-degree angle.
Yep.
Place that right angle vertex anywhere on the circumference of the circle. The 2 legs of the square will then cross the circle at 2 other points.
Okay.
The line segment connecting those 2 points, that's always a diameter of the circle.
Wow.
So just do that twice, placing the square at different spots on the circumference. You get 2 diameters. Where they cross, that's your center. Bam.
That is incredibly clever. A practical application right there. But Casey's forward thinking doesn't stop, does it?
Yeah.
He broadens the idea of an angle itself, going beyond Euclid. He does. Euclid generally stuck to angles less than 2 right angles, less than 180 degrees. But Casey starts preparing the student for things like trigonometry and mechanics. He explains how modern geometry allows for angles greater than 4 right angles, more than 360 degrees, or even negative angles.
How?
By thinking of angles as rotations. You can rotate more than a full circle or rotate in the opposite direction. It's a much more dynamic concept.
Right, needed for physics and engineering.
Absolutely. And while we're on circles, here's a little puzzle from the question section in Casey's book. How many common tangents can 2 circles have?
Common tangents. Lines that touch both circles, I guess, 2. Maybe 4 if one's inside the other. No way.
It depends. Depending on how they're positioned relative to each other, they could have 2, 3, or even 4 common tangents. It's a nice visual problem.
Huh. Okay, book 4 then gets into polygons. And Casey makes an interesting observation here. Every proposition in the 4th book is a problem. Why is that significant?
It's different from the other books, which mix theorems, proving things, and problems, constructing things. Book 4 is purely about construction. It's all about how to build specific regular polygons. Think equilateral triangles, squares, pentagons, hexagons, inside or around circles, using only the classical tools, a compass, and an unmarked straight edge.
Ah, the classical constructions.
Exactly. And tuck away in the exercises for this book is one of the real gems of elementary geometry, the 9-point circle.
The 9-point circle, I've heard of that. It sounds almost magical. 9 specific points all lying perfectly on one circle.
It really is remarkable. And these aren't just random points. They are very specific points related any triangle.
Okay, lay them on me. Which 9 points?
All right, yeah. First, the 3 feet of the perpendiculars from the vertices to the opposite sides, those are the altitudes endpoints.
Okay, 3 points.
Second, the 3 middle points of the sides of the triangle.
Right, midpoints, that's 6.
And third, the 3 middle points of the segments connecting each vertex to the orthocenter. The orthocenter itself is where the 3 altitudes intersect.
Got it. Midpoints of the lines to the orthocenter, that makes 9. Wow.
It's a beautiful, beautiful example of hidden order in geometry, all neatly arranged on one circle.
That genuinely is incredible. And another maybe simpler fun fact from book 4, the side of a regular hexagon inscribed in a circle
Is just equal to the radius of the circle.
very neat, very elegant.
It is. And Casey's notes section, which is full of these extra insights, mentions an even bigger breakthrough related to constructing polygons.
Oh, what's that?
He mentions Gauss. Carl Friedrich Gauss, the mathematical giant. Centuries after Euclid, Gauss figured out precisely which regular polygons could be constructed using only compass and straight edge.
Like the ones Euclid showed.
Yes, but Gauss proved it was possible for others too. Most famously, the regular 17-sided polygon, the heptadecagon, something nobody had suspected before. It showed geometry wasn't a closed book.
Wow, 17 sides. Okay, so moving on. Book V starts getting into the elegance of proportion, ratios, areas. But Casey himself says something pretty direct, almost blunt, about Euclid's original proofs here.
He does. He states quite plainly that Euclid's original proofs of proportion, while ingenious, possess at present none but a historical interest. He even says no student reads them now.
Harsh. So throw them out.
Not quite, because he immediately follows up by saying that Euclid's propositions, the results, the statements about proportion, are still, quote, by every writer, and his nomenclature, his terminology is universally adopted.
Okay, so the methods change, but the ideas stuck.
Exactly.
Yeah.
The way we prove things about ratios evolved, especially with the development of algebra, but the core concepts in the language Euclid established, they're timeless. They remain the foundation. It's about the substance, not just the original proof technique.
That makes sense. The concepts endure, and one of those fundamental concepts is incommensurable quantities. Can you unpack that a bit?
Sure, these are quantities where their ratio just can't be expressed perfectly as a fraction, as the ratio of 2 whole numbers. The classic example is the diagonal of a square compared to its side. That ratio is the square root of 2.
Right, an irrational number.
Exactly. You can't write or 2 as a simple fraction like PQ. Casey explains that we deal with these by approximating them using convergence, fractions that get closer and closer to the true value. We can get as nearly as we please to the exact ratio.
Which sounds a lot like limits in calculus or modern numerical methods.
Precisely. It connects directly to how we handle irrational numbers and approximations today.
So building on that understanding of proportion from Book 5, how does Book 6 then use these ideas when looking at similar figures? What's the key principle Casey highlights about how their areas relate?
Okay, so Book 6 really brings it home. The core idea is that similar figures that have the same shape but possibly different sizes, relate to each other proportionally, yes, but their areas relate by the square of their corresponding sides.
The square.
Yeah, so if one triangle is twice as big as a similar one in terms of side length, its area will be 4 times bigger. Casey points out this is the first time Euclid uses the term duplicate ratio, which basically means the ratio squared.
Okay.
And Casey, being Casey, actually offers a simpler proof using the ratio of the squares idea directly, rather than Euclid's more complex original approach. Again, showing his focus on making it understandable. And this applies not just to polygons, but also to circles and sectors of circles, too.
That's a great example of his teaching approach. And Book 6 also contains that famous extension of Pythagoras' theorem, right? Proposition XX=1.
Ah, yes. A beautiful generalization. It's that if you take any right-angled triangle and you construct any set of similar figures on its 3 sides, not just squares, could be similar triangles, semicircles, anything, then the area of the figure built on the hypotenuse is equal to the sum of the areas of the 2 similar figures built on the other 2 sides, the legs.
That's really powerful. It takes Pythagoras way beyond just squares.
It really does. It shows the depth and interconnectedness of these geometric ideas. From 2D, Casey then guides us into the third dimension, the geometry of solids in Book 11. He starts with something that seems really basic, but is foundational. One part of a right line cannot be in a plane, and another part not in it. Seems obvious, but how does Euclid prove it?
Yeah, how do you prove something that feels self-evident?
With pure logic. He uses an elegant proof by contradiction. Assume it could happen, part of the line is in the plane, part is outside, then you could extend both parts. And you'd essentially have two distinct straight lines intersecting in more than one point, or enclosing a space, which Euclid already established is impossible.
Ah, relying on previous results, that rigorous chain of logic.
Exactly, that's the bedrock.
Yeah.
And in 3D, Casey properly defines key terms like dihedral angle.
Angle between two planes, like an open book.
Precisely. And solid angle, which is formed where more than two plane angles meet at a point, like the corner of a box or a pyramid.
Got it. And the appendix to Casey's book gets into calculating volumes and surface areas, prisms, cylinders, cones.
Yep. He starts with right prisms, like a box or a Toblerone package stood upright. The volume is simply the area of the base times the altitude, the height.
Straightforward enough.
And he shows how you can slice any prism into triangular prisms to prove this holds generally. Then he extends the idea to cylinders. Volume is pi times radius squared times height, and cones. He notes that a cone's volume is exactly 1/3 of the cylinder with the same base and height.
1/3. Okay. And then comes a real aha moment, right? Something about a sphere and a cylinder that fits around it.
Oh, this is a classic, often attributed to Archimedes, who is apparently very proud of this discovery. If you take a sphere and imagine the smallest possible cylinder that can perfectly enclose it, its height would be the sphere's diameter, and its base circle would match the sphere's equator.
Okay, the circumscribed cylinder.
Exactly. The volume of the sphere is exactly, beautifully, 2/3 of the volume of that circumscribed cylinder.
2/3. That's surprisingly neat.
It is, and it gets better. The sphere's surface area is also exactly 2/3 of the total surface area of that same cylinder, including its top and bottom lids. It's this stunningly simple ratio connecting these two fundamental shapes, a real highlight.
Wow. Okay, so stepping back and reflecting on all this, Casey's addition was clearly a big deal in its time. What does this tell us about his legacy and maybe the nature of geometry itself?
Well, the success is undeniable. The preface mentions the rapid sale of former editions, selling each 3,000 copies, which was significant then, and its general adoption in schools. It obviously hit a nerve, filled a real need.
It bridged that gap.
It did. It took the timeless foundation of Euclid and made it accessible and relevant for students grappling with emerging mathematical ideas.
And the reviews cited in our source material are incredibly positive, praising its simplicity and neatness of style, the sheer number of carefully arranged exercises, nearly 800. That's a lot of practice.
Yeah, and they highlighted his elegant but eminently suggestive alternative proofs, and those notes of great interest that apparently contain material not easily accessible elsewhere. It sounds like it was incredibly comprehensive and thoughtfully put together for its audience.
A truly forward-thinking textbook for the 1880s.
Absolutely. And one of those fascinating notes sections goes into the famous problem of the quadrature of the circle, squaring the circle, and the nature of pi.
Ah, pi. What does Casey say?
He explains clearly that pi cannot be expressed as the ratio of any two whole numbers. It's irrational. But crucially, it can be approximated to as many decimal places as may be required. He even gives a nod to a Mr. Shanks who, at that time, had calculated pi to an astonishing 707 decimal places.
707, wow. That shows the ongoing human drive for precision, even with these ancient concepts.
Definitely. It underscores that geometry, even based on ancient foundations, is a living, evolving field where new depths are constantly being explored.
So to wrap up, we've taken this deep dive into Euclid's Elements, but specifically through the unique lens of John Casey's 1885 edition. We've seen how he didn't just reprint it, but actively reimagined and enhanced it, creating that bridge between ancient wisdom and more modern mathematical thinking.
Yeah, and looking at it this way really highlights that geometry isn't some static, dusty subject filled with old proofs nobody reads anymore. Well, maybe not Euclid's original ratio proofs.
Right, right.
But it's a dynamic field. It's built on rigorous foundations, sure, but it's full of elegant solutions, surprising connections like the 9-point circle, and concepts that keep evolving.
It really makes you think, doesn't it? How these foundational geometric principles, worked out by Euclid, refined by people like Casey, expanded over centuries. they still underpin so much of our world.
Hmm.
Computer graphics, architecture, engineering, even how we model the universe.
Absolutely fundamental.
So here's a final thought for you, our listener. What modern technologies or just everyday phenomena do you encounter that fundamentally rely on these seemingly abstract elements of geometry we've been discussing today? Something to ponder.